Number 10. The Great Attractor. In the direction of the Centaurus and Norma clusters lies one of the most mysterious gravitational anomalies ever discovered. Located roughly 200 million light-years away, its influence reaches us even now. Our entire galaxy, along with tens of thousands of others, is surging toward it at over 2 million kilometers per hour. This motion is not random, nor is it caused by local gravitational interactions. It is a large-scale cosmic flow, as if an unfathomable force is pulling entire galactic clusters toward a single, unseen point in space. Yet we cannot see it. The Great Attractor is hidden behind the zone of avoidance, a dense shroud of gas, dust, and stars within our own Milky Way that obscures visible light. We are attempting to map one of the most massive structures in the observable universe, while remaining partially blind to its nature. Astronomers suggest it may be the focal point of the Laniakea supercluster, a gargantuan gravitational basin. But even with infrared and X-ray data, its exact mass and structure remain uncertain. What makes this truly unsettling is that the expansion of the universe should be driving galaxies apart. In our local cosmic neighborhood, however, something is powerful enough to override that expansion. We are moving toward it. We cannot stop it, and we do not fully understand what it is. Number 9. Fast radio bursts. In 2007, astronomers analyzing archival data stumbled upon a phenomenon that lasted less than the blink of an eye. A sudden burst of radio waves, only milliseconds long, yet carrying immense energy. In that brief moment, it released more energy than our sun emits over several days. Initially dismissed as mere interference or a local glitch, more bursts were soon detected, originating from distant galaxies billions of light-years away. Then the mystery deepened. Some of them repeated. This is where the problem begins. Most high-energy astrophysical events like supernovae are violent, one-time occurrences. They do not repeat with structure or rhythm. Yet certain fast radio bursts return again and again, some even displaying periodic behavior, emitting signals in cycles like a cosmic heartbeat. While magnetars, neutron stars with extreme magnetic fields, are a leading explanation, they fail to account for all FRBs, especially those with such precise timing. Nature, at this scale, is not supposed to behave like a clock. We are detecting signals from across the universe, and we still cannot fully explain what is broadcasting them. Number 8. Dark energy. For most of the 20th century, the scientific consensus was that the expansion of the universe would gradually slow down as gravity pulled everything back together. In 1998, that assumption collapsed. Observations of distant supernovae revealed that the universe is not slowing down, it is accelerating. Galaxies are receding from one another faster over time, as if the fabric of space itself is being stretched by an invisible force. This force was labeled dark energy, but the name is a placeholder for our ignorance. It is a label for a phenomenon we cannot explain. Current estimates suggest that dark energy accounts for nearly 70% of the total energy content of the universe. This means everything we understand, matter, stars, and galaxies, comprises less than a third of reality. Dark energy cannot be detected directly. It emits no radiation and does not interact with matter in any measurable way. We only infer its existence through its effect on cosmic expansion. This creates a deeply unsettling reality. The majority of our universe is made of something undetectable and unknown, and this mysterious force is deciding the ultimate fate of everything in existence. Number 7. The cold spot. When scientists mapped the cosmic microwave background radiation, the oldest light in the universe, they expected a nearly uniform temperature across the sky. Instead, they found something that defies our cosmological models. A massive region of space, spanning nearly 2 billion light-years, is significantly colder than its surroundings. This anomaly, known as the cold spot, was initially dismissed as a statistical fluke. But as measurements improved, the cold spot remained. One potential explanation is a supervoid, a vast region containing almost no matter. However, light traveling through such a void cannot fully account for the magnitude of this temperature drop. This has led to more radical hypotheses, including the idea that the cold spot is evidence of a collision between our universe and another during the early stages of cosmic inflation. While there is no definitive proof, the fact that such a hypothesis is taken seriously highlights the gravity of the problem. We have found a signature embedded in the oldest observable light in the universe that we cannot fully explain. Number 6. The black hole information paradox. A fundamental principle of physics is that information cannot be destroyed. It is a cornerstone of quantum mechanics. Black holes, however, appear to violate this rule. When matter falls into a black hole, all information about its structure and quantum state seems to vanish beyond the event horizon. According to general relativity, nothing escapes that boundary. Then came Hawking radiation. Stephen Hawking discovered that black holes are not entirely black. They emit radiation and slowly evaporate over time. If a black hole eventually disappears, what happens to the information it once held? If the information is destroyed, quantum mechanics is fundamentally flawed. If it is preserved, our understanding of gravity and black holes is incomplete. This is not a minor inconsistency. It is a direct conflict between the two most successful theories in physics. Whether through the holographic principle or information encoded on the event horizon, we are left with a paradox at the heart of reality. Either our understanding of gravity is wrong, or our understanding of quantum mechanics is. Number 5. Tabby's star. Roughly 1,500 light-years away. In the constellation Cygnus lies a star that defies stellar logic. Officially designated KIC 8462852, it first drew attention through data from the Kepler Space Telescope. While stars typically dim in predictable patterns when planets pass in front of them, Tabby's star is different. Its light drops dramatically and irregularly, sometimes by more than 20%, with no consistent cycle. Initial theories pointed to natural causes like comet swarms or massive dust clouds, but these struggle to explain the sheer depth and randomness of the dimming. This led to the controversial suggestion of a Dyson swarm, a massive artificial structure built by an advanced civilization to harvest the star's energy. While most scientists favor natural explanations, the alien megastructure idea was considered precisely because conventional models were failing. Even today, Tabby's star is not fully understood. It serves as a reminder that when data does not fit our current understanding, the truth may be stranger than we can imagine. Number 4. Cosmic voids. On the largest scales, the universe resembles an intricate web, with galaxies forming filaments and clusters. Yet, between these structures lie vast regions of near-absolute emptiness, cosmic voids. Some of these voids span hundreds of millions of light-years, containing almost no galaxies or matter. While matter is not expected to be perfectly distributed, the problem is the sheer scale. Some voids are far larger and emptier than our best cosmological simulations predict. According to our current models, gravity should have clumped matter together in a way that avoids such extreme gaps. Furthermore, these voids are not static. They expand and merge, reshaping the structure of the universe itself. This raises a fundamental question. Are our models of post-Big Bang evolution incomplete? These voids are not just empty space. They are regions where our scientific predictions begin to fail. When the largest structures in existence do not behave as expected, it suggests we are missing a core piece of the cosmic puzzle. Number 3. Ultra-High-Energy cosmic rays. Detectors on Earth occasionally register particles arriving from space with energy so extreme they challenge the known laws of physics. These particles carry energies millions of times greater than anything produced in our most powerful particle accelerators. However, established physics dictates a limit to this energy, the GZK cutoff. This principle predicts that interactions with the cosmic microwave background should drain the energy of such particles over long distances. In short, these particles should not be able to survive a long journey across the universe. Yet, we detect them. This leaves us with two possibilities. Either these particles are coming from nearby, unidentified sources, or our understanding of high-energy physics is incomplete. With no confirmed origin for the most energetic events, we face the uncomfortable possibility that the universe can accelerate matter in ways that are currently beyond our comprehension. Number 2. The Hubble Tension. Measuring the expansion rate of the universe. The Hubble constant should be a straightforward task. Instead, it has become one of cosmology's greatest crises. There are two primary measurement methods. One analyzes the early universe via the cosmic microwave background. and the other measures distances to nearby galaxies using supernovae and Cepheid variables. Both methods are backed by decades of rigorous research, yet they do not agree. This discrepancy, known as the Hubble Tension, has persisted despite increasingly precise observations. Scientists originally suspected data errors, but as the measurements improved, the gap remained. This leads to a troubling conclusion. The problem may not be our tools, but our model of the universe itself. Resolving the Hubble tension may require entirely new physics, or a fundamental revision of how we perceive cosmic expansion. Until then, we are forced to admit that we may not understand how the universe truly works. Number 1. Boltzmann Brains. This concept arises not from direct observation, but from the unavoidable mathematics of statistical mechanics. In a universe that is infinite in size or exists for an infinite duration, random fluctuations are inevitable. Given enough time, particles could randomly arrange themselves into any complex structure, even a fully functioning human brain. These hypothetical Boltzmann brains would materialize in the vacuum, complete with thoughts, memories, and a sense of self, only to vanish instantly. While it sounds absurd, some cosmological models suggest that Boltzmann brains would vastly outnumber biological observers like us. This leads to a disturbing statistical implication. It is mathematically more likely that you are a random fluctuation with false memories than a biological being with a real past. While we don't claim this is true, the fact that our laws of physics allow for such a possibility forces us to ask, how can we be certain that our experience of reality is real at all?